Alrighty, so today we're going to continue to talk about some of this surface integral Stokes theorem stuff, and I think honestly this is probably the trickiest material all class. The stuff we'll do next week people usually find to be a little bit easier to understand, so keep that in mind. I guess that's a relief if you're really feeling confused now. But let's just briefly review the basic setup formulas for surface integrals just to make sure everyone's on the same page. So the first important thing to keep in mind for surface integrals is that there's two kinds. There's when you have a scalar integrand and when you have a vector field integrand. So let's just separate these. So this is the flux of a vector field, which remember is basically measuring how much your vector field arrows are passing through your surface. Whereas this one, you have a scalar integrand. And what you want to think of, if f is the boring constant function 1, then this first kind of surface integral gives you your surface area. And so that's something we've had for all our types of integrals in this course, that when you integrate the boring constant function 1, you get the size of the region of integration. And by size, for one-dimensional objects, that's length. For two-dimensional objects, that's area. For three-dimensional objects, that's volume. So we always have that sort of thing happening. Otherwise, you want to think of, if you have an interesting integrand that's not just the constant function 1, think of that as being the density of something on your surface. So maybe your surface is a thin metal sheet, and parts of the sheet are made out of aluminum, parts of it are made out of lead, and it's sort of blended together so that there's heavier parts of the sheet and lighter parts of the sheet. So you have some sort of mass density that's distributed on this sheet. When you do that surface integral, you get the mass of the sheet. And you could also think about this in physics class. You might have talked about charge being distributed on a sheet of some sort. You could think about the surface S as being the surface of the Earth, and we're looking at population density on Earth and things like that, if you're really taking the curve of the Earth into consideration. But yeah, all kinds of stuff you could do with that. Okay. And so as far as actually calculating it, this is where it gets a little bit more different from the line integral situation. But anyway, if we have a parametric equation R of uv for this surface, and we want to set it up that way, then the formula would be the double integral of f of R of uv times the length of RU cross RV dA. So you want to think of this as being d big S. And I think Dom talked about this a little bit in lecture, that essentially you want to think of this length of RU cross RV as being like a stretch factor. That it gives you the relationship between area in the UV plane with area in the XYZ plane. Because the whole idea is you want to think about this equation R of UV. It takes some domain D that lives in the UV plane. You're plugging it into this R of UV, and then that spits out a surface S that lives in XYZ land. And so then the idea is that depending on the behavior of this R of UV, you have this little rectangle of points in UV land being sent to a little patch on your surface. And so ds is basically the area, measures area on the surface, whereas dA measures area in UV plane. And so this length of RU cross RV, that stretch factor, is giving the relationship between these two areas, is the way you want to think about it. Okay, so anyway, that's that. But then often we won't have our surface S given to us in terms of R of UV. Often our surface will be a graph of a function of two variables. So remember, the graph of g of xy, so I'll put graph of function of two variables. So if your surface is instead given to us like this, you could go through it, set up R of xy as x, y, g of xy, like we talked about last week, and go through all these calculations. Or you could just memorize that in this case, you end up getting, just make sure you plug in for z, that z is g of xy. And then this stretch factor becomes the square root of 1 plus gx squared plus gy squared. And that's what we end up getting. And so again, yeah, in this graph situation, d big S is that. And so in this case, this stretch factor, in this case, first of all, note that no matter what, it's greater than or equal to 1, because we're squaring gx and gy, so the thing we're taking the square root of is always at least 1. So first of all, it's always at least 1, and it's the relationship between area on the surface and area of the shadow. Because when your parameters are x and y, you don't have to go outside to abstract UV land to understand what's going on with x and y. X and y, this region D, is really the shadow of S in the xy plane. And we've talked about this shadow idea before. But anyway, we can really illustrate this idea that the areas are different just by playing around with some pieces of paper. So what I'm going to do is I'm going to take this piece of paper and fold it in half, let's say. And I can situate things like this, such that if I were to stand directly above, so I'll show you this angle. This is tricky. But the idea, play around with this with your own sheet of paper. You can situate things so that when you look down from straight above and think about the shadow of this diagonal piece of paper, that you just simply see this. So this is the shadow of this situation here. And by shadow, we're always imagining in this context to have the light shining straight down. But anyway, yeah, you can have this so that this whole sheet of paper is directly above this. I guess here, I can just do it right here by, hiding it perfectly behind like that. And so anyway, the only way that they have the same area is if this is lying horizontally. So if as soon as I start rotating this up so that it's not horizontal, the shadow is actually going to shrink. And so that's one way you can think about this going on. But yeah, that's what you want to think about this RV cross RV length, or this square root. It's something that relates areas between different things. Okay, but anyway, that's the first kind of surface integral. And then the second kind of surface integral looks like this. And so it's the flux of this vector field. And so we have to be doing flux across oriented surfaces. Oriented surface basically means that you've labeled one side something and the other side something else. So for example, I always like to think about it as whatever, Penn State. You've painted one side of your surface blue and you've painted the other side white. And so when we're asking about flux, we have to be saying flux from the blue side into the white side, or vice versa, the flux from the white side to the blue side. You could also think about flux of what that represents. If this F is a fluid velocity field, it's the volume flow rate of velocity, or I guess it's the volume flow rate of fluid across a surface, or I guess I should say through a surface. And the fluid has velocity field given by your vector field. So remember, that was one of our other interpretations of vector field arrows, is that's the, you can imagine it being ocean currents or air currents around an airplane wing or something like that. And so if you think about these units here, if this is the velocity of something, it's going to be length per second. And then this is going to have units of area, so that the units of the flux in this context would be meters cubed per second. So that's what I mean by volume flow rate. So for example, let's say I had the window in my office open and it was a really windy day. The flux of air through the window would tell me how many cubic meters of air per second are blowing in from the outside. And so, you know, let's say there's 2 cubic meters per second coming in, that's the same as -2 cubic meters per second going out. But the whole idea is that we've had to label the sides of the window, or the situation here. We've had to label the outside versus the inside, and that's really what's going on with this orientation. And so it turns out that there's some pathological surfaces that you can't label the sides of coherently. There's that Mobius strip that somehow has that little twist so that the two sides sort of become one. That locally it seems to be fine, that you have one side and you have the other, but then something pathological is happening with the larger scale structure and how the sides sort of merge together. So you can't do flux across a Mobius strip or anything else, but yeah, we're not going to worry about that in this class. All the surfaces that we'll deal with will be oriented without trouble. And so anyway, the formulas for flux are going to be similar, that we'll have a general one that works for the general parametrization, S in terms of R of UV, and so that one you get F of R of UV dot product with the cross product RU cross RV. And so again, this ds vector is a vector quantity. So we haven't taken the length of this cross product in this situation. And we leave it as a vector, and then we do the dot product with our vector field F. Okay, and then we also have a graph shortcut. And so in this case, F, remember P, Q, and R are our default component names for our vector fields. And so if you were to go through it, set up R of xy is x, y, g of xy, do these partials, do the cross, then do the dot product, you get this formula. And so I found, I think it's a good idea to memorize this formula and get used to using it and get comfortable with it as much as you can. So yeah, let me try to write that a little bit nicer. Okay, yeah, let me just start over instead of trying to sneak it in the middle. So minus pgx minus qgy plus r. Okay, and so the other reason I really like this graph shortcut formula is that the orientation you can correct by multiplying by -1 if you were going with downward. So the situation with orientation, it's part of the question, right? If I said how much air is going through this window, I'm not really specifying if I'm talking about in versus out. So in a well-formed question, the orientation is part of the question. And so with Z graphs, upward versus downward always will work. Upward doesn't necessarily mean straight up. Upward just means that all of the k components are positive. And so if you start to think about, okay, well, for z equals g of x, y, could I ever have a situation where the k components switch sign? And the answer is actually no. Like, this is a perfectly fine surface, but this is not a z graph because it fails the vertical line test, that there seems to be multiple values of z for the same values of x and y. So anyway, if you're curious about this, upward versus downward are always the two choices for z graphs. As far as orientation goes, if you're using this formula, when you get here, you have to make sure this is correct. This is consistent with the orientation in the problem. That, remember, the whole idea of this orientation, it's encoded by unit normal vectors at each place. Given a surface, your two choices for unit normals would be just directly perpendicular, length 1, and then that narrows it down to two choices. Really, it's the same idea as you're painting one side blue, the other side white. And so you'll have to make sure that this RU cross RV vector is consistent with the orientation that you're given in the problem, and that's a little bit annoying. So essentially, I try to do this whenever possible. Okay, so anyway, we'll eventually take a look at an example, but I guess I want to mention here as well, you could also do y equals g of xz or x equals g of yz. Depending on the surface that you're given, it might not be best suited for a z graph. You might have y as a function of x and z, or x as a function of y and z, and you can sort of adjust this formula as necessary. Okay. So anyway, let's see if we can find the outward flux of the vector field, xy9, across the boundary of the solid region enclosed by the cylinder, x squared plus z squared equals 1, and the planes y equals 0 and x plus y equals 6. So I think I might have rotated it, but I tried to do a parametrization of this type of surface. I guess it would have been last week's recitation. The last video that I did, which, when would that have been? Maybe it was last Tuesday. Anyway, I did an example sort of like this, so we'll get practice parametrizing it again. But then we're also going to want to set up and go through the flux on each of these pieces. So anyway, the boundary of the solid region enclosed by the cylinder, x squared plus z squared equals 1. That is a cylinder around the y-axis, right? And then y equals 0 is, of course, the xz plane. And then x plus y equals 6 is going to be some kind of diagonal plane. So yeah, we're going to be looking at something sort of like this, that we have this other plane, x plus y equals 6. And so at the end of the day, we're left with this surface that consists of three pieces. So it says it's the boundary of this solid region. And it says outward flux, so we have to go outward away from the points surrounded by these three things. So outward on this whole thing means leftward on the left-hand boundary, rightward on the right-hand boundary, and then away from the y-axis on that piece. And so we have to start thinking about how to parameterize this. So let's call S1 that piece, S2 that piece, and then S3 is the side piece. And so what we saw when I showed you this example before is, yeah, the first piece, S1, it's a piece of the XZ plane. So let's just do it as a simple G of XZ. Like Y is G of XZ. In this case, it's pretty boring. It's just Y equals 0. And then what are the parameter values that give us this? Well, it's the unit disk. And then I could say leftward, or I could say negative Y orientation to indicate that the outward flux, we have to orient that part of the surface away from the positive x-axis. So that's what we're going to want to do for S1. For S2, we have a slightly more interesting G of XZ. But we have the same parameter domain that X and Z belong to the unit disk. Okay, and then that has positive Y orientation. And then this last one, the sort of the trickiest one, if you remember, the idea was we think cylindrical coordinates, but slightly altered cylindrical coordinates where we left Y alone. I think in the example I showed you, I might have done this where all this action was around the x-axis. I don't remember exactly, but this time, this cylinder that we're dealing with is around the y-axis, so let's convert x and z into polar. And then realize that x squared plus z squared equals 1 corresponds to r equals 1, so that our parameterization for S3, we can use y and theta as our parameters. And since this cylinder has radius 1, x and z are cosine theta, sine theta, and then y is just y. So this, yeah, definitely the trickiest of these three pieces. Okay. And then in this case, for D, theta is going to go 0 to 2 pi, and 2 to we're going all around. And then what's y doing? Y is going to stop once it reaches that plane. So y starts at 0 and stops at 2 minus x, sorry, 6 minus x, but x is cosine theta in this case, remember? Because this r of y theta is just x, y, z. And then the orientation here is away from the y-axis. Okay. So these are our three pieces. So S1, flux on S1 and S2. We're going to use a Y-graph shortcut. So I'll show you where this comes from, but then I'll also show you how, if you memorize the Z-graph shortcut, you can, without too much trouble, sort of figure this out. So anyway, both S1 and S2, Y is given as a function of X and Z. Those are my parameters that I'm using, X and Z. So if I wanted to set up a parametrization, that's what I would be dealing with, that R of XZ is X, G of XZ, Z, so that Rx is 1 GX0, RZ is 0 GZ1, and RX cross RZ is, well, in this case, it's going to be GX minus 1 GZ. And notice that this, I guess it's because I cross K is minus J, this is sort of the negative Y direction. Because notice this K component is -1, which means that for positive Y orientation, you would want to use minus GX1 minus GZ, and then when you go to do F dotted with that, so I'll write it as RZ cross RX is the positive Y1. That's where you would get minus PGX plus Q minus RGZ. So by going through and setting up this parametrization and doing this dot product, you get it. So I'm running out of space. I'm just going to write down the result and then show you how, if you memorize it from the Z-graph situation and alter it, it just makes perfect sense. So Y-graph shortcut, if S is given by Y as a function of X and Z for X, Z in D, and with positive Y orientation, the flux formula for F, well, I'll just write it as PQR dotted with DS is minus PGX plus Q minus RGZ. And I guess I should put, for positive Y, just think about there being a little plus sign there. So if it was negative Y orientation, you would just multiply by -1. And so anyway, if you look at this, this follows the same pattern that the Z-graph shortcut has. So for Z-graph, you think to yourself, okay, Z is special. So Z is the third variable, which means that R, the third component, is by itself. The other two components have a minus as well as a partial derivative with respect to those variables. So if you practice this minus PGX minus QGY plus R, get really comfortable with that, then when you switch to Y being special, you're like, okay, well, Y is the second variable, so the second component Q is by itself. The other two components have a minus, and they have partials with respect to the appropriate variables. So again, that's how I like to suggest you deal with this, sort of get real comfortable with the Z shortcut and then just alter it as necessary for something like this. But if you really wanted to, you could go through those steps that I erased, where you just set up the parameterization, do the partials, do the cross, and go from there. Okay, so anyway, let's get going. So for S1, S1 has a pretty simple g of xz. So gx and gz are both 0. So for S1, our formula is going to be minus x times gx plus y, but y is 0, minus r is 9 times 0. Because the whole idea is that this dA is dx dz in this situation. So I guess there's something I should point out as a little extra thing to be careful of. That this dA is dy dx or dx dy, which means that you have to replace z with g of xy. That's really the only thing that makes sense to do, because on this surface, z is g of xy. So replace z with g of xy in PQR. Because remember, Z could be in your vector field, but it's not allowed to be in this dy dx double integral because our answer needs to be a number. So replace Z with G of XY in PQR. So that's the same thing that needs to happen here, that in this situation, this dA, this double integral is with respect to our parameters, which for the y graph are x and z, which means that I need to replace y with g of xz, because my answer has to be a number. Okay, but yeah, so that's our PQR. So Q is y, and y is 0 on S1. So anyway, you end up getting double integral of 0. So you get 0 on S1. On S2, ooh, and I guess it doesn't make a difference because minus 0 is still 0. But remember, S1 has negative y orientation. So I have to put a minus out front here. Okay, and then S2, I have a slightly more interesting g of xz. G of xz is 6 minus x, so gx is minus 1. So S2, I'm doing the double integral of minus p gx plus q. But q is y is 6 minus x. And then minus r gz, well, gz is still 0, because g of xz for S2 is 6 minus x. And so looks like the x's cancel, and I'm doing the integral of 6 across over the unit disk. I know the area of the unit disk is pi 1 squared, but yeah, figure that out as however you need to. Okay, and then finally S3. S3 is going to be a little bit trickier because S3, I guess I could do it as a graph if I really wanted to, solve for Z on the top and bottom halves, but that would introduce even more work. So S3 is a situation where I'm just going to do it with y and theta as the parameters. So to get things going, I'm basically going to be using this formula. I need to start doing Ry, R theta, so minus sine theta, 0, cosine theta. And then Ry cross R theta is cosine theta, 0, minus sine theta is sine theta. And so if you remember a few minutes ago, I mentioned you have to make sure that this is consistent with the orientation in the problem. So is this vector cosine theta, 0, sine theta, does that point towards the y-axis or away from it? It does in fact point away from it. So for example, think about the vector cosine theta, sine theta in the xz plane. Our cylinder, the shadow in the xz plane is just that circle, right? That's the trace. And so does this vector point towards or away? Well, if theta is acute, both cosine and sine are positive. So when theta is a first quadrant angle, cosine theta, sine theta points that way. So I could have very easily, I think when I did this in class a few months ago, I randomly chose to do r theta cross ry, which of course points in the direct opposite direction, which means that that's the wrong choice. So that's the downfall of not using a graph shortcut. I mean, you can't always use a graph shortcut, so you should be open to this. But you have to make sure that this ry cross r theta points the right way, and it turns out that it does. So then we're able to continue f of r of y theta. Well, f was x, y, 9. So x is cosine theta, right? Because this is x, y, z right there is r. X, y, 9. And then f dotted with ry cross r theta is whatever, cosine squared theta plus 0 plus 9 sine theta. And so then I'm doing the integral 0 to 2 pi, 0 to 6 minus cosine theta of cosine squared theta plus 9 sine theta dy d theta. And so I'm not going to do that double integral. It's not so bad. I guess you'll need you'll need a double angle identity to help with cosine squared. And then you'll also have a cosine cubed that you have to deal with. But the trick for cosine cubed is if you write cosine cubed as cosine squared times cosine, that's cosine theta minus sine squared theta cosine theta. So if you use the fact that cosine squared is 1 minus sine squared, so Pythagorean theorem, then you have that, and then you can hit it with a, if you're interested in integrating, I'm not going to write the d thetas, which means I'm going to erase this because I don't want to leave bad notation like that. But if you hit it with a u equals cosine, or I'm sorry, u equals sine theta substitution, it works out because then du is your cosine theta d theta. So anyway, yeah, cosine cubed, that's the trick for that. You might remember that from 141. I don't think we'll make you do cosine cubed on a quiz or exam without a hint, so don't worry too much about that. What I really want you to get out of this problem, yeah, because obviously I don't think we're going to put something as tricky as this with so many little steps in a multiple choice form. So understand more the fact that there are 3 pieces, that we can parameterize each piece like this. So we might ask little questions like this, but we're not going to ask you to put all this stuff together. Your final answer for this homework question would be 0 plus 6 pi plus whatever that integral ends up being. So anyway, that was a doozy, but that goes to show how sometimes we can use altered versions of this z-graph shortcut, or sometimes we might need to use this general formula. All right. So that's surface integrals. Let's get into Stokes' theorem, the other tricky thing, probably the trickiest thing all semester. So I think the trickiest thing about Stokes' theorem is the fact that we actually use it in 2 different problem situations, whereas one we're kind of going in this direction, whereas the other we're sort of going in that direction. And then we might go back, but it's tricky. So I think that's best illustrated in the difference between, if you look at problems 14 through 17 and 19 on this week's homework versus problems 11 through 13. I don't know why the book puts them in the order that they do. I find 14 through 17 and 19 to be a little bit easier for everybody to understand, whereas 11 through 13 is a little bit of a trickier concept. But anyway, let's take a look. So 14 through 17 and 19, the question goes as follows. It says, find the work of F, and it so happens that C is a closed curve. And so closed curve F dot dr, you should already be thinking Green's theorem from a couple of weeks ago, I guess last week. And that's Green's theorem is the case for closed curves in R2. So now we're sort of expanding our horizons to be talking about work integrals for closed curves in R3. And so that's the general question for problems 14 through 17 and 19. And so then the idea to solve it, I'll just do it in blue just so it's different, is that you use Stokes' theorem in this direction that says the work of F is equal to the flux of curl F. So on a closed curve, the work of F is the flux of curl F, where S is any surface with boundary curve C. So that's the general approach for 14 through 17 and 19. Whereas 11 through 13, the question is find the flux of a vector field, not just any vector field, but the flux of curl F. So next week, when we finally learned the last section and we're putting all this stuff together, even more so than we are now, there's special properties you're going to be wanting to look out for. So this is the special property in this situation, whereas this is the special property here. So last week when I talked about curl and divergence, not every vector field is curl of something, in the same way that not every vector field is the gradient of something. Remember, being a gradient is special. It means your curl is 0. It means that you have an anti-gradient. Not every vector field has an anti-gradient. We talked about that a lot. So similarly, not every vector field is curl of another vector field. So the fact that this is written like this, that's the special part. So the idea then is that Stokes' theorem basically says that, well, I can do the work of the anti-curl. So in some sense, you could say that that's what Stokes' theorem says if you're thinking about this direction, that the flux of some vector field on a surface is the work done by its anti-curl on the boundary curve. So you're sort of using Stokes' theorem in the other direction. It's still true, and it's still fine. Or you could use Stokes again to do the flux of curl F across S1, where S1 is a simpler surface with the same boundary curve as S. So you're not going to do both of these. But if we ever ask you to do the flux of curl F, what we're wanting you to do, we're not going to tell you to do it, but we want you to realize that you're supposed to do the work of F on the boundary curve or the flux of curl F across a simpler surface. So you can't just change surfaces for any flux question. You can for flux of the special vector field curl F, because not everything is the curl of something, but if it is, then this is okay. And so I think Dom has hinted at the fact that this whole chapter, we're just learning the same thing in different contexts. It's actually the fundamental theorem of calculus. But I want to draw a strong parallel to something we talked about a couple weeks ago with this idea. So this next slide, path independence of work of conservative fields, surface independence of flux of incompressible fields. So, okay. This first thing, the situation was, let's say I have a start point and an end point, and I have some curve C, and I have some curve C1. For most vector fields, for general F, the work of F on C is not equal to the work of F on C1. So if you want to think about, I mean, friction is more complicated since friction depends on velocity, but intuitively you should know that if you have non-conservative forces, the work done depends on the path that you take. So for example, let's say I have, I don't know, let's say I have a book and I'm trying to get it from this point to this point. Let's say they're both on my desk. And let's say for some reason the desk has some crazy Velcro type stuff. Maybe the book has some crazy stuff on it, so that the friction, if I try to directly slide it along the desk, takes a tremendous amount of effort, okay? If that's the case, then it might be easier for me to just lift the book up and then go through the air and bypass that friction against the table and then plop it back down. So when you have non-conservative forces, it might take different amounts of energy to get from point A to point B, depending on which path you take. So for general F, the work done, so remember F is just a bunch of arrows. It looks like the work on C is positive, F dot dr, but then on C1 would be negative. So for general F, the path you take affects your answer for F dot dr. But for curl F equals 0, that means that F is the gradient of a scalar function, and that the work on C is equal to the change in the anti-gradient. And that's the same thing for C1. So for special vector fields, not all vector fields have 0 curl. Remember, we could play around with Clairaut's theorem to understand why 0 curl is important for having an anti-gradient. I should say that things are continuous on appropriate regions, but we're not on that one day with limits when we allow pathological behavior, so just assume everything's continuous everywhere, differentiable, all that fun stuff. When you have 0 curl, you do have an anti-gradient, and the fundamental theorem of line integrals justifies this. So fundamental theorem of line integrals tells us that. Okay, so we have something similar now for this, that let's say I have some curve C. Let's say then that S is, well, let's say that S1 is that surface. So the S1 is, let's say a disk. And let's say that S is a hemisphere. I don't know if Dom talked about SOAP and blowing bubbles and fun stuff like that. But the way I like to think about Stokes' theorem is you have this curve and you have a surface that has that curve as its boundary. So I like to think about the curve as being a wire, like sort of your bubble wand. And then you dip your wand in the soap, you're about to blow some bubbles, and your surface is any way that the soap could be stuck on that wand. So it's before you blow the bubble, the soap might be just sort of stuck flat on your wand, right? You dip your wand in soap and there you go. But then let's say you start to move your hand then the soap sort of forms like a hemisphere-like shape. It's still stuck on the wand, it hasn't detached yet, but that's the idea, is that you want to think of these surfaces S as being any way that you could have soap stuck on a bubble wand, C. And so anyway, if I have two surfaces that share the same boundary, so that's the same idea, is the curves sharing the same boundary. What is the boundary of a curve? Well, the start and the end point. So we're just kind of scaling up this boundary idea in another dimension. What are the points on the edge of the disk, the circle? What are the points on the edge of the northern hemisphere, the equator? It's the same. So for general, I'll just call it vector field G. The flux of G across S is not equal to the flux of G across S1. In general, the surface matters. You can't just change a hemisphere into a disk and expect to get the same flux. However, for div G equals 0, so that's what we said was incompressible, means that there's zero divergence. It turns out that that tells you that G is the curl of something, or G has an anti-curl, in which case curl F across S is the work of F on the boundary curve C, and that's equal to, again, by another application of Stokes' theorem, the flux of curl F across S1. So it's the same exact phenomenon, that when your vector field has the appropriate special property, you can change the surface to be something similar. So this is Stokes' theorem, and this is special. But for special, and so this here is Stokes, as is, the other one. And so, like I said, Dom's been hinting that we're just learning the same fundamental theorem of calculus every situation. So any sort of fun observation we have on one level is going to have another one later on. So all this stuff is tied together. And so this is what we're exploiting. That for problems 11 through 13, because I'm asking for the flux of a special vector field, and so we'll usually give you this hint that it's special. For conservative, we don't usually tell you it's conservative. That's up to you to figure out, but for if it does have zero divergence, we will sort of give you that hint by writing it as curl F. So as soon as you see the flux of curl F, then you're looking to say that, oh, that's either equal to the work of F on the boundary curve or the flux of curl F across a simpler surface. So that's the idea. If you're going to eventually solve this, you're exploiting this surface independence of that. So anyway, that's the concept. Okay. So the key idea here is C and C1 share start and end points. S and S1 share the boundary curve C. So there are two different ways soap could be stuck on a bubble wand before you've blown the bubble, before it's detached. Okay. So let's do these questions. Let's do the easier one first. So find f dot dr, where C is the boundary of the part of the paraboloid in the first octant. Ooh, and I guess I should say counterclockwise from above. Forgot to include that. Okay. So anyway, why is Stokes' theorem useful for this? We'd have to do a direct calculation. F dot dr, we did that 2 weeks ago. So, okay, our curve, we have this paraboloid that opens down from z equals 1, but then we're looking at the part of that paraboloid in the first octant. So it's going to look something like this. And counterclockwise from above, we'd have something like that. So the boundary consists of 3 pieces. So for a direct calculation, I'd have to do C1, C2, C3. And C1 is basically part of a parabola in the YZ plane where x is 0. So I'd have to do R of t is, well, x is 0 this whole time. Let's let y be t, and then z is going to be 1 minus t squared, and this is going to be from t equals 1 to t equals 0 to make it go in the correct direction. And then C2, I would have R of t. Well, now I'm living in the xz plane, and t equals 0 to 1 is going to take care of that. And then C3, that piece, the intersection of the paraboloid with the xy plane, and then that thing, that's a quarter circle piece. So I don't want to deal with square roots. I'm going to do cosine t sine t 0, t equals 0 to pi over 2. So this is kind of tricky. All these 3 pieces live in a coordinate plane. So usually getting formulas for R of t for curves in space is trickier. Usually line segments is about the best we can do. But if we carefully think through this, we could do that. And then you'd have to do f of R of t dot product R prime of t for each. And so that's fine. That's what you would have done 2 weeks ago if this question turned up. But anyway, I think getting those R of t's, I think you all should be able to do it, but I recognize that I think I did lose some people with some of that. I know some of you are looking at that, you're like, wait, how in the hell do you get those R of t's? And plus, this seems pretty tedious as far as having to do this 3 different times. Instead, let's use Stokes' theorem. So the better way is to use Stokes to do one flux integral instead. So Stokes' theorem says when you have work of a closed curve, you can calculate the flux of curl F across any surface that has that as its boundary. And so this is sort of the trickiest type of surface I that we usually deal with. Most of the other surfaces you'll see in the homework are pieces of planes. So there's no plane that has this curve C as its boundary, the two parabola pieces and the circle piece. However, the paraboloid has it as its boundary, because I mean that's how it's given to us, that boundary of the part of the paraboloid. That's a huge hint that that's what we want to use for S. So what we're going to trade this in for is the flux of curl F, where S is the part of Z equals 1 minus x squared minus y squared in the first octant. And there's this right-hand rule that's sort of going on that makes sure we have compatible orientations between our curve and our surface. But the most common situation that you can just kind of get used to remembering is that counterclockwise from above on C corresponds to upward orientation on S. Rain? Anyway, so let's get this set up. I need to figure out curl F. So del x, del y, del z, and F is x, y, z, xz. So 0 minus y, 0 minus z, 0 minus x. Okay. So I'm doing the flux of minus y minus z minus x. So this is where you have to be careful. I'm going to then use the flux shortcut formula for this z graph, where p, q, and r are the components of whoever's flux I'm taking, which is not f in this case, it's curl F. So when I go to use then this minus p gx minus q gy plus r, that's the flux formula. So P, Q, and R is the flux of whichever vector field we're trying to compute for, which is not F, is curl F. So you do have to be careful with that. But anyway, looks like we get minus P, so minus y times gx is minus 2x minus q. Remember, we have to do everything dy dx, so substitute z is 1 minus x squared minus y squared every time that turns up. So minus q gy plus r. And so then at this stage, I think you're going to want to convert to polar coordinates. It's a little bit of a pain, or not a pain, well, it's a little tedious. So anyway, it's the part of, in the first octant, so the xy shadow is this quarter disk. So you'll do 0 to 1, 0 to pi over 2. So I'm just going to put a minus outside for everything. I'll have a 2r squared cosine theta sine theta plus 1 minus r squared times 2r sine theta plus r cosine theta, but then everything gets hit with an extra r when we switch to polar. and then just kind of go from there. So I think I showed you, you can parameterize in terms of R and theta, but then you have to go through, do the RR, R theta, RR cross R theta, check that it's upward. That's why I don't like doing that. So anytime you can use a graph shortcut, I really recommend it. It just makes a lot of things easier. So upward, I know that I'm doing things correctly by using that formula. Okay, so anyway, that's that. And then the last problem I wanted to look at was 13. So notice, yeah, these are both coming from the Stokes theorem section. And you have to, ASAP, really start paying attention to what's being asked and pay attention to all those little details. I know that we've been learning a lot of stuff and your head's probably spinning, but you're going to want to pay attention to all the little details. So the previous question we did was asking for the work of F. This one is asking about the flux of curl F. So it's a different type of question. It's related. It's still going to utilize Stokes' theorem for the best solution. But those are the details you're going to want to pay attention to. So I think as it turns out, there's 9 different problems from chapter 16. And basically, it's going to be up to you to figure out which of the 9 problem types you're dealing with and go from there. So I think probably the second lecture is what I'll kind of go through, one of each of the 9. It'll be sort of a long marathon, but we'll go through. Here are the 9, here's the things you look for, and this is the best way to proceed. So that'll probably be on Tuesday. And so yeah, these are different types. This is one type, find the work of F on a closed curve C. This one is find the flux of curl F. And so flux of curl F is our other Stokes situation. And so what we're going to do is something like up here. We're either going to do the work of F on the boundary, or we'll do the flux of curl F on that. So, okay, let's try and visualize this situation. Find the flux of curl F. S is the top and 4 sides of the cube with vertices, blah, 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 oriented outward. So let's try and draw this. So there's no bottom. And so, okay, we're asked to do the flux of curl F. Okay. And so if I asked you to do this after Monday's lecture, when we just learned about flux, you could have done this, except it's a little bit annoying. You'd have to do 5 pieces, right? Because dealing with each of these pieces would be tedious. So for example, piece 1 would maybe be the part of z equals 10 for x and y between minus 10 and 10 with upward. And then piece 2 would be the front piece, x equals 10, for y and z between 10 and negative 10, with positive x orientation, and so on and so forth. But yeah, it's 5 pieces, right? It's 5 different squares. And so yeah, you could do the flux on each of those and add them up. Okay, but then the benefit is Stokes' theorem, because it's the flux of curl F. You can't, in general, you can't remove a curl. Not every vector field has an anti-curl. Not every vector field is the curl of something. But when it is the flux of curl F, that allows you to use Stokes' theorem to say, you know what, the flux of curl F is the work of F on the boundary curve. If any of you get into meteorology or aerospace, the flux of vorticity is the circulation of velocity, is what's being said here. But anyway, we have to then figure out what the boundary curve C is in this case. So upward on S, because the top has up, sort of tells us, yeah, counterclockwise from above is what we're looking at. I guess this would be 10, 10, minus 10 if you start thinking about these points. This would be minus 10, minus 10, minus 10. And then this would be 10, minus 10, minus 10. So, okay, you could do F dot dr, but you'd have to do 4 line segment pieces, which is fine. But I think the best way for this is to do another round of Stokes' theorem, which says that, okay, this thing here, that's not the simplest way that the soap could have been stuck on this square, right? The points on the edge are this bottom square. I can much more easily have a surface S1 be the piece of Z, the plane Z equals minus 10 for X and Y, both between minus 10 and 10 with upward orientation. So essentially what we've done is, you could sort of think what we've transformed this complicated soap, it's sort of morphed and flattened out to be like that. And usually you can't change surfaces, but it's the flux of curl F, which means that you actually can. So that's going to be the best way to proceed here, is to do the flux of curl F across S1. So why is S1 so great? So I think Dom talked about this. What day would it have been? Probably Monday this week. I'm allowed to choose this very simple g of xy, whose derivatives are 0. So when I go to do this flux formula, so minus p gx minus q gy plus r, P and Q, the first 2 components of curl F, are getting multiplied by 0. So we don't even have to calculate what they are. I could do that curl F is, I don't care. Remember, the third component of curl F is our familiar old, I shouldn't mix what P and Q refer to. But essentially, to get the third component of curl F, I do the x partial of that minus the y partial of that, which is going to be y minus xz. So calculate your curl. So I'm doing the double integral from minus 10 to 10, minus 10 to 10 of y plus 10x. So remember, z is minus 10. We're doing a dy dx double integral. So if you have z, you're going to be in trouble. And then it turns out at 0, because this, now I'll go through and do it. This rectangle has symmetry both over the x-axis and the y-axis. The first term is odd with respect to y. Second term is odd with respect to x, so it ends up being 0. But that's the idea. Okay, so I think you're going to want to practice this, work on the homework, come back to this. This is definitely the most challenging material we've had. The last section, the last idea, the divergence theorem, is not nearly as bad. Turns out if you have the flux of any vector field on a closed surface, you could do the triple integral of the divergence. So divergence is easier than curl because it's a scalar function. Curl is kind of a pain in the ass, right? So that's one reason why divergence theorem is easier, is that the divergence is not a vector anymore. It's a scalar, so that's easier. And then second of all, I think triple integrals people are a little bit more comfortable with than surface integrals and line integrals. That I think Stokes' theorem is particularly tricky because, you know, last week we gave you this object f dot dr, this line integral, and then earlier this week we told you about this flux integral, and then now we're telling you that certain times this flux integral is equal to that work line integral. So I think it's just a lot of new concepts all at once. So that's why we wanted to make sure we got through that this week so that next week we could do divergence theorem on Monday. Like I said, I think in general people find that a lot easier to understand. And then Tuesday for the second half of next week, material we could just spend reviewing, catch our breath. And like I said, Tuesday I'll have one problem of each of the 9 types, 9 approaches I should say, 4 problem types, 9 approaches. And yeah, we'll decide how to do them. But anyway, have a good weekend, and I'll see you on Monday.